Okay, good afternoon, everyone. My voice is still not completely back, so I apologize. So today we're going to talk about how we train these neural networks. There's a few things that are going to be different than what we've seen until now. The first is how we run gradient descent if we have a really big data set. So, as we know, when we want to train our model, we have some parameters theta, we have some cost, we'll call it script j. This would be the negative log likelihood. We want to minimize this to get our maximum likelihood parameters. And the form of this cost is like this. This is going to be the average of these sample-wise costs or losses. So this is like, for the ith pair xi, yi, this non-script j will be the one that works on the pairs, and then the script j is going to average over the entire data set. Okay, so what we learned to do previously was to do gradient descent. We do something like this. The new parameters equal the old minus a small positive step size times the gradient of the loss with respect to the parameters. And if we apply the gradient to this expression due to linearity, we can move the gradient through this sum, and we have like the averaged gradient of a particular pair. Now, when you look at this expression, you realize that to do a single iteration of gradient descent, of which there may be many thousands, you have to compute the gradient for all n samples in the data set. If your data set is small, that's not an issue, but if your data set is large, that can be super expensive. So if we're dealing with MNIST, we have like 50,000 training samples. These for every little update to my parameters, I have to compute 50,000 gradients. And a lot of other real-world data sets are much worse. There's millions of samples in the data set. So the main issue with this is that computing the gradient is very expensive when the number of training samples is large. Even more than that, if you think about how gradient descent works, typically, this is just still a toy example, but if I have a quadratic loss like this, and I start over here, I don't move directly to the minimum. I move perpendicular to the contours, which takes me in sort of a curved path. So if you think about that original gradient direction, it's not even pointing at all in the right direction, right? It's just pointing quite a bit far off from the direction we would ideally like to go in. And so, why should we spend so much effort computing this gradient that's not even pointing in the right direction in general? Why don't we just approximate this gradient computation to get us something that's close? And maybe that's going to be good enough. Maybe, if I can reduce the computation of this to something that's like 1/100th, then I can take 100 steps with the same effort, and I'm going to get a lot farther than this one very precise gradient step. Does that idea sort of make sense? Why the gradient is expensive and why spending all that effort to compute it is probably not even worth it? Okay, so that's the main idea behind what we're going to propose. So it's not really clear that it's worth the effort to compute it precisely. So we're going to use something called mini batches. So what you do is in each gradient descent step, rather than using the entire training data that you have, use a small subset of the training data. So in a picture, maybe this is your matrix of training data, And let's assume that we've shuffled the rows of that matrix. So all these entries are shuffled. And now if I pull out a little chunk of it, that would be a mini batch. The size of this chunk sort of depends on the application. Maybe it's like 100 samples. Depending on how big each sample is and how much memory you have to work with, it could be as small as one sample. But it's just some subset of the overall size of your training data. And then we'll give this a name. We'll call the subset of indices I, we'll call that capital I. So this is a subset of the indices from 1 to n. And at every iteration, we're going to use a different subset. So this subset will vary with the iteration index t. But we'll assume that it always has the same size. So it's always 100 samples. Okay. And so basically the idea is we will compute an approximate gradient where we average over this subset instead of using all samples. So here in the sum, rather than going I from 1 to n, we're just taking I from that subset. And instead of dividing, multiplying by 1 over n, we're multiplying by 1 over the size of that subset. So we're just approximating this gradient. And then once we have that, we'll call it G, the approximate gradient. Then we can just run gradient descent in the same way as before, but now we're using G, the approximate gradient, in place of the true gradient. So every gradient descent step is now going to be a lot cheaper to compute because we have to compute far fewer gradients and average, for far fewer samples for every gradient descent step. So that's the idea. Is that making sense? Any questions on this? Okay, so we want to think about this set as random. So we're going to pull out a random set. You could also say like you used a random shuffle, and then, for that, once you've used that random shuffle, now you can pull out deterministically these chunks. But because that set is random, that set of indices is random, so is this approximate gradient. That is now a random vector. And this algorithm is called stochastic gradient descent because G is a random approximation of the true gradient. Okay. Sometimes this is called mini batch gradient descent. Sometimes people use stochastic gradient descent to specifically mean the case when you only pull out a single sample, but we're just going to use stochastic gradient descent for this general case where you have some random subset of indices, and you use only those to compute your gradient. Okay. Any questions on this idea? It's pretty clear? Okay. So the question is can we analyze this? Turns out we can, and it's pretty easy. So the question now would be okay, we know this approximate gradient is not equal to our true gradient because we're not using the full set of samples, but is it good in some average sense? Is it unbiased? Is it correct on average? We can answer that question by looking at this, analyzing this quantity. What is the expected value of the gradient vector given the previous parameters in this gradient descent update? Because I need those parameters there to actually compute the gradient of each of those pairs. So if what we do is we just plug in this expression into here, and then we'll do one other trick where instead of writing the sum this way, where I is in the set, we're going to write the sum over all I, but then we're going to include this thing called an indicator function. This is going to take the value 1 whenever I is in the set, and if I is not in the set, this will take the value 0. So that means that at the end of the day, this does exactly the same thing as this. For any I in the set, it sums over that I, and for any I not in the set, you don't see that I show up in the sum. But the reason this is nice is because now we can think of the randomness really occurring here. So we said that I was random, but we said that the size of that set I is fixed. So even though I is random, this is fixed. So the only thing random in this whole expression is really this set here. So what we can do then is we can bring the expectation in. We're conditioning on this, so this is deterministic too. And we can bring the expectation just to this guy. And then we're asking the question, essentially, how often, if I have some fixed index I, let's say I equals 1, in a random set, capital I, how often is that fixed index in that random set? So let's say, for example, the random set is half of your samples in your full training set. And you're looking at the first sample as I. The question is, how often will I be in that random set? Well, half the time, because it's just this capital I is half of the full samples. Or if the capital I is 1/10 of the full samples, and you're asking how often is the first index in that, it would be 1/10 of the time, and so on. So basically, the expected value of this is just going to be the size of I over n. And that's it. So you do that expectation. These sizes of I cancel to give you 1 over n here. And all of a sudden, you have back the exact gradient, a true gradient. So what this says is that on average, this approximate gradient is correct. It equals the true one. So it's unbiased. So that's a nice justification for using this method. Okay, so anytime you pick this G, it's never going to equal this, but on average, it's doing the right thing. Okay, so let's see, any questions on this step? Okay, so we found out that their gradient is correct on average. What about the updated parameters? Theta t plus 1. So what we can do is we can plug in this expression for this. So we get this. Then we're conditioning on theta t. So this is deterministic, step size. We'll say that that's fixed. So really this expectation just comes down to this, and we already computed that. So we plug that in and we find that, okay, on average, the new parameters are exactly the same as if we had used full gradient descent. So it doesn't, on average, there's no error brought to those true parameters. Okay, so overall, you get a picture sort of like this. If on the left, we have gradient descent, slowly converging down to the minimum, then on the right here, we have a picture of what you might have. There's actually a couple pictures in there. Let me try to. Okay, so one of them is if you have a large step size. This is what stochastic gradient descent might look like. As you can see, at every iteration, it's taking you in some direction which is not the gradient direction. But then the next time, it's another random direction that's off, and then the next time, another random direction. But overall, you are progressing slowly towards the minimum, right? And each one of these is going to cost a fraction of computing this one. So maybe, if you could make 10 of these, you can see how much farther you got than one of these, which might have the same cost. Now you can go further. You can say, well, all right, maybe one way to think about it is it's like this approximate gradient is the true gradient plus some noise that is zero on average. It's zero mean. So this noisy gradient, is there a way to kind of filter out that noise? And the answer is yes. You just decrease the step size alpha t. If you decrease the step size, it means you just use less of this for every change in theta t. And that means you only see a little bit of that noise at every iteration. And over many iterations, that noise sort of averages out and gets close to zero. In that case, you have this line that's underneath, which is maybe something like that. So again, it's not this perfect, smooth gradient trajectory, but you can see that it's a lot closer to the true gradient trajectory. This especially matters when you get close to the minimum, because if you're the red trajectory, and in fact, if you initialize the red trajectory exactly at the optimum solution, because the gradient is not the true gradient, it will push you off and it will push you away. And you will keep bouncing around, and you will never settle there. You'll just keep bouncing around forever. Whereas, as we know with gradient descent, once you get down closer and closer, your gradient steps get smaller and smaller. If you ever get to the true solution, you just stay there. You don't leave. So what's nice about this blue line is that because of this averaging effect, you get close to the solution and you bounce around in a much smaller region. You don't fluctuate as much. And so this is how you can control the size of that fluctuation, is to use a smaller step size. And in fact, a more sophisticated scheme would be to start out with a large step size, which brings you quickly close to the minimum. And then later, you reduce the step size, which means you fluctuate less and less, and you sort of focus on the minimum. And so you can do that if you have a step size that changes with time. Sometimes people say just use alpha t equals 1 over t. In that case, you can prove a lot of these algorithms converge. Okay, so that's the idea behind stochastic gradient descent. Gradient's correct on average. You have this gradient noise, but you can deal with it by excuse me, reducing the step size alpha t. Okay, so that's a new trick that we have that really speeds up convergence when we have a large data set. Okay, questions on this? This is making sense? Yeah.
Isn't the true gradient on the left would be noisy based on the sample length?
Noisy based on what?
Because of sample noise, even if we consider like every single sample,
What is sample noise?
the epsilon that, well, we know that when we draw samples from a distribution, you don't get.
We're not drawing any samples from a distribution.
Fair enough.
We just have a loss function. Right? We have this. We're just trying to minimize this. It's deterministic. So, so we run this algorithm, and as long as this loss is convex, we'll get there. What's different here is this approximate gradient is not the gradient of the loss anymore. It's some approximation of it, which is not correct, which means that instead of behaving like this, we do something else. And in fact, that something else we're doing is random. So that's really the difference between these two. Okay, any other questions? Okay, great. So a few implementation details and notation. So let's say, as usual, we have n samples in our training data set. So from now on, we'll say we have b samples in each mini batch, and we'll assume that the mini batches do not overlap with each other. So that means that we would need capital T mini batches to cover, capital T equals n over b mini batches to cover the entire training data set. So this is, this would be n, this would be b, and so the number of these required would be T is n over b. So like 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the way that you typically run this is okay, so let's see. So essentially, okay, we use one SG iteration per mini batch. And so if we go 10 iterations, we'll use all of our training samples exactly once. And we'll call this set of T iterations one training epoch. Okay, and so the way that this is implemented is you think in terms of epochs, where you go through the entire training data set, and you think about batches, or mini batches, as what happens within an epoch. And so for each epoch, what you do is you randomly shuffle all your training indices. Just imagine you shuffle everything. Now that it's shuffled, for that epoch, you can take things out in chunks. First, second, the third, and so on. So this would be first iteration, second iteration, third iteration, all the way down to the Tth iteration. Now you're in the next epoch, and what you do is you reshuffle to get a completely different order. And after you reshuffled, you can just once again take out the first B, the second B, and so on. And because you reshuffled, you can be sure that this subset is going to be different than any of the other ones you've used until now. Okay, so that's what you do for each epoch. You randomly shuffle all your training samples. You partition those shuffled indices into these T contiguous subsets. We call them IT. And we use subset IT to compute the gradient and cost in SGG iteration T. Then we go through all those iterations until we're done with that epoch. And then we start the next epoch. And in terms of how many epochs you use, you just have to sort of monitor your overall loss. If your overall loss looks like it's done converging, that's when you stop. If it looks like you still have progress to be made, you keep cycling through more and more epochs. Okay. All right, is this procedure making sense? Any questions on this? Okay. Okay, so that essentially concludes this SGD mini batch idea. The next thing to start talking about is how we compute the gradients, because this is now a lot trickier than before. So just to remind us, in this 2-layer neural network, the parameters we have to adjust are the weights in the hidden layer matrix, the intercepts in the hidden layer, the weights in the output layer, and the intercepts in the output layer. So you can see there's a lot of parameters that must be learned. We said we can do stochastic gradient descent like this, but now essentially we have to figure out how do we compute this gradient term over here. So for the purpose of this part, we will define this sum without any averaging, just to keep the averaging out to be simpler. So we have a sum of the cost over our different items in our mini batch, and we'll call this script j at iteration t. And the cost itself depends on the iteration because the mini batch samples depend on the iteration. So this is t dependent, and of course the parameters are also t dependent. Okay, so the question is, how do we compute this gradient? This is what's complicated, so we'll spend the rest of the lecture talking about this. So, like I said before, in this course we want to bring our calculus down to scalars because scalar calculus is a lot easier than vector calculus. So for scalar calculus, the things we need to compute would be the partial derivative of this with respect to all the entries in this WH matrix. And so those would be the scalar entries WH, L, J, where L would be the row and J is the column of this matrix. Okay, so there's a whole bunch of these we want to compute. Then we want to compute the gradient with respect to this, which means the partial derivatives with respect to all of its entries. So BHL, where L indexes through that vector, we have to compute the gradients for all of those L. And similar for all of these elements of that matrix and all the elements of this vector. So these are all the things we need to compute, and you can see there's quite a lot of them. Okay, so when we go forward, we're just going to simplify the notation a bit. We're going to drop all mention of t because essentially what we do at every iteration t is going to be the same. So there's nothing t dependent about it. So we'll just forget about t for the moment. Okay, so the first thing to talk about is how we're going to kind of think about and order our computations. So for this, we're going to be using something called the computation graph. Computation graph is just showing how the different variables depend on each other. So here I use some color coding. So the data set, the observed variables, we have x and y. We know those. At the beginning of this gradient descent iteration, we know the parameters w and b from the previous iteration. So that's like theta t. The things we don't know yet until we compute them are the hidden layer scores, the hidden layer activations, the output layer scores, and we will assume that there's no output layer activations just because we know that they're optional. We don't actually need them. And we're just going to do without them for this, for all of what we say next, just because it's simpler. Okay, so that means that our loss is written in terms of the output layer scores, not the output layer activations, just something to take note of. Okay, so does the idea of the computation graph make sense? So basically, like, this is what it's saying. It's saying that if you want to compute the hidden layer scores, well, they depend on xi and these parameters. So if you know this stuff, you can compute this stuff. Once you know this, you can compute this. Once you know these things, you can compute these. And once you know these things, you can compute this. So what we'll do is we'll start with the things we know, and we'll move from left to right, and we will sequentially compute the things we don't know, parameter, all the variables, and then finally we'll compute the cost on that mini batch. This is called the forward pass. Once we're done at the forward pass, we will know the values of all these variables. At that point, we will go from right to left, backwards, and we will compute the gradients. First, the gradients with respect to this, then the gradients with respect to this, and this, this, and this, and so on. That is called the backward pass. The forward pass is very straightforward because all we need to do is push our data through the equations that we've seen before. So if you remember from last week, these are the equations. So to compute the hidden layer scores, you just need to put the ith data sample through that WH matrix, add the intercept terms, and you have the hidden layer scores. You actually will do this separately for each of the indices in your batch. So I'm assuming here we have a batch size of B. So we'll just say I goes from 1 to B. And so we just do this B times for different I. Then, to go from here to here, we just put those scores through our activation function to get our activations. And remember, this activation function, you can see this is written lowercase. This is a scalar function that operates independently on each entry in this vector to get each entry in the left vector. So the first entry of this is used to compute the first entry of this, the second to compute the second here, and so on. There's no coupling between those entries. Once we have these hidden layer activations, we can now compute the output layer scores according to this. Here you can see that there is a mixing between the entries because we have a full matrix multiply. So that means, for example, the first entry in this vector here depends on all of the entries in this vector because they get multiplied by all the first row of this matrix. So these matrix operations, they do mix things together, whereas this activation function does not. Okay, and finally, once we have the output layer scores, we can combine them with our labels to compute the cost first for each element in our batch, and then we'll sum that over the batch to get our final cost for the batch. Okay, so this is the forward pass. Simple as that. Any questions on that? Okay. Next, we'll talk about the backward pass. The backward pass is a lot more complicated. So what we're going to do is we're going to go in small steps. First, I'm just going to recall the chain rule and point a few things out about the chain rule. Okay, so this is just the chain rule that you learned a long time ago in your first calculus class. So let's say that I have a variable z that is some function of y, and y is some function of x. So if I want to compute dz dx, we all know that you do that by dz dy times dy dx, just like this. Right, this is what we do all the time when we're computing derivatives. Now, if I keep everything the same, but I somehow introduce some new temporary variable, I'll call it u, and now, it's maybe x and z are exactly the same. I'm just sort of almost changing the notation by putting in this other, calling out this other new variable u in the middle. And so you might wonder, well, okay, does that really change anything? So, intuitively, dz dx should be the same. Nothing's really changed, and that's actually true. One way to think about this is the overall dz dx, you could write as dz du times du dy times dy dx, just like this. But then again, using a chain rule like this, you can say, oh, well, this product is nothing more than dz dy. So if I plug that in, then I'm right way back to this. So the moral of the story is when you compute these chain rules, you do not have to involve all the variables in between if you don't want to. If somehow, you've computed dz dy and you've computed dy dx, you can then directly compute dz dx without ever worrying about u. It doesn't really help you. Okay, so we'll see that as we go forward. All right, any questions so far? This chain rule stuff? Okay, the other thing we talked about somewhat recently is the multivariable chain rule. So the idea here is we have a computation graph where these are scalars. And let's say that these yi are scalars, but there's a whole bunch of them right here. So I'm using the bracket notation to say there's actually a whole bunch of yi. I could also maybe draw the picture a little differently. For example, maybe I could put a bunch of nodes like that and then put arrows like that to say that in some sense the information flows through these different yi's to go from x to u. That's another way to sort of visualize what's happening here. So anyway, in this case, we know that dz dx, well actually, we have some freedom in how we do this. We can think of that as I drew it here, or if I didn't want to involve u, I just wanted to say u is not really that helpful to me, I could also just kind of take u out and directly draw some lines to z. And then I could do the following. I could say, all right, to do dz dx, I can use these intermediate variables, but I have to sum across all of them. So that's where you get the multivariable chain rule. So dz dx is dz dy1 dy1 dx plus dz dy2 times dy2 dx plus dz dy3 times dy3 dx and so on. And that's where you get this. Okay, so it's really sort of a matter of seeing all the different ways that the information flows through this computation graph and making sure that you include all these different paths when you compute that gradient. Okay, so those are the main things to keep in mind. And with these tools, we can attack our computation graph, which is quite a bit more involved than these. All right, any questions on any of these rules? All right, so let's try this. We're actually going to try it 3 times in increasing order of difficulty. The first time, we're going to make it as simple as possible. We're going to make all the variables scalars. There's no vectors or matrices. And we're going to make the batch size 1. And that means that there's no sets of variables. These are just single scalars. In which case, our computation graph reduces to this. And the forward pass reduces to those 4 equations. So basically, like you take in x, scalar feature, multiply it by this weight, add the bias, you get this scalar score ZH. You put ZH through this scalar function activation to get AH. Then you put AH, you multiply by the weight, add the bias to get output Z. And then there's only one batch element, so the script J is the same as this non-script J. Okay, so that's the forward pass going through here. And before the forward pass, we know these variables, but after the forward pass, we know all the variables in the network. We know what all of them are. We've computed them. Okay, so now let's talk about the backward pass. So we're going to start at the right side, and we're going to move our way left. So the first thing we'll figure out is, what is dj dzo? Yes. So we look at the equation that relates those variables, and from the equation, it's pretty clear. D script j dzo is just going to be whatever this is. You know, that could be squared error, it could be binary cross entropy. Whatever that is, you just take the derivative of it at the location zo that you computed in the forward pass. So this is the thing we want to compute, and this is what it is. We have this function, we evaluate that function at the variable that we now have a value for. So we have now dzdo. Now that we have that, we move farther. Next, we want to do dj dah. We can see that we can use this part of the computation graph. We can do dj dzo times dzo dah. So this is the equation. Now this part, we already computed this. We actually have a physical value for that. So we just plug in whatever that number is here, and we multiply it times this. Okay, for this, we have to do a little bit more work. So what is dzo dah? Well, we look at the equation. We see it's pretty straightforward. dzo dah is just WO, right? And WO is a value we know at the beginning of this iteration. So that's just a number we know. This is a number we know. Multiply them together, and now we know this number. Now we go a little further. I want to do DJ DZH. But I can leverage the fact that I have already computed DJ DAH. The only extra work I have to do is this. Multiply it times DAH DZH. Okay. So this thing I know from before. Just like this thing I knew from before. So now all I have to do is figure out this. So I just look at the equation. Okay, this is the equation. So now DAH DZH, well, that's just going to be whatever function this is, its derivative, evaluated at ZH. So ZH is something I computed in my forward pass, so I know that. I can, I know what the derivative of that function is, so I can compute that. I get this number, I multiply it times this number, and now I have this number. Okay, so now I have established all these different derivatives along this kind of backbone here. Are you sort of seeing the pattern? Okay. Now the things we really need to compute are actually the gradient with respect to the parameters. Those are the things we need for gradient descent. So let's first do DJ DBO. So for that, we have this little part of the computation graph. That would be DZO times, DJ DZO times DZO DBO. So DJ DZO is something we already computed above, so we know that. Now DZO DBO, we look over here, we can see DZO DBO is just 1. So that's simple. So now we can just multiply those two numbers together, and we know this. So we will use that in gradient descent, this iteration. We also want to get DJ DWO. So again, we do DJ DZO times DZO DWO. This thing we already computed. This thing is not too bad. We look at this equation, see DZO DWO is just the value AH, which is itself something we computed in the forward pass. So now we multiply this times this, and we know DZ DWO. And so now we have the gradient with respect to the output layer parameters. Any questions on this? All right, now to get these are the hardest, they're the deepest ones. Well, it's actually no harder because we did this intermediate computation already, DJ DZH, and now we can do DZH DBH. So this is computed above, and DZH DBH, we just look over here, DZH DBH is 1, so that's easy to compute. And the last step, DJ DZH DZH DWH, over here, we know this from above, and then this one, DZH DWH, that's just going to be X. So now we have all of our parameters that we need for gradient descent. So then we do gradient descent. We get some new parameters, new W's and B's from gradient descent, and we start this over again. Now we involve the training data. We do the forward pass to learn these, backward pass to learn the gradients. Then we do another gradient descent step, and so on and so on. And this whole thing, backpropagation, as you can see, it takes something that would be really complicated. If you just wrote this out into one gigantic mathematical expression, it would look super intimidating. But by sort of breaking it up into this computation graph and just going step by step, you can solve anything like this, no matter how complicated it is. As long as it has this sort of tree structured form, it's just a turn the crank procedure, no matter how complicated the architecture of that neural network is. Okay. All right. Any questions on this case here that we've seen? Is this kind of making sense? Or does it seem difficult? What do you think? Should I move on, or should we discuss this one more? You guys are one of the more quieter classes I've had, so I'm not sure whether to just keep going or pause. Okay, so no questions? All right, so let's move forward then. So now, let's make things a little bit more complicated. We'll keep everything scalars, but we'll increase the batch size, which means that we have a whole bunch of different features, xi, where I goes from 1 to b. That's what those curly braces mean. We have, consequently, a bunch of these hidden scores, b of these, hidden activations, hidden outputs, and labels. However, we only have a single copy of the weights and biases, or weights and intercepts for the 2 layers. Okay, so we start with the forward pass. Just go through these equations. They're the same as last time, except now we have indices I on the z quantities and the x quantities. So we evaluate this for the different items in our batch. We evaluate this for the different I. And again, it's important here to notice that there's no mixing across different values of I. Like when I is 1 here, that does not affect any other activations except for the I equals 1 activation. So that's important when we consider below whether to use the multivariable chain rule or not. Okay. Down here, we have the linear stage in the linear part of the output stage, and we have to do this separately for all the different I. And finally, all the samples I in our batch get combined together to get our overall loss. Okay, so we said we went through the forward pass. So now we know all the variables in the computation graph. So next we want to go do backpropagation. Okay, so the first thing is, and let's do scalar calculus, so not try to handle all the batch, like pack them into a vector and try to handle that. No, we're just going to do separately for each of these individual i's, dj dzo I. So this is the ith entry in the collection of outputs of our network. So we look at this equation, and here you can see I've written this with I prime. Actually, there's a little, this should be a prime too. Sorry about that. I've written that with I prime so that we don't get that I confused with this I. So when I take the partial derivative of this with respect to this I, there's only one of the I primes that matters, and it's the I prime that matches this I. So there's only one of these terms that matters. It's the one with I there, and we take the derivative of that, and we get this. So I guess I omitted the notation here, but so there would be a yi there. Okay, so that's done. Next, we want to do dj d dahi. So here we want to be careful. So I'm focusing not on this entire batch, but just one element in the batch. So the question is, do I need to use the multivariable chain rule or not? Because we do have a bunch of variables, it seems, here. But if I focus on one batch index, do we have multiple variables here or not? What do you think? There's just one, right? Like, let's say I equals 1. So I'm looking at the first entry in my batch, and we're saying, okay, how do these variables interact? It comes from this equation, which says if I'm looking at a particular I here, this only affects exactly one of these ZOs. It does not affect all the ZOs, it just affects the ZO with the same I. So that means if I focus on a single one here, there's really a single one here. I don't have a bunch of them. And so I don't have to use a multivariable chain rule. There's only one way the data flows, not several parallel ways. Okay, so that means that when I do the chain rule, I don't have to use the multivariable one. I can just fix I, and I use I everywhere. So dj dzoi, dj dahi is dj dzoi times dzoi dahi. So this we already computed here. And this equation, this derivative we get from here. And you can see no matter what I is, dzoi dahi is just wo. So that's what that is. Okay. Now I do this for the different i's because these will vary over I, and so I'll get different values for different i's, but the way I compute it is just the same for each one, and there's no summation here. Okay, is that idea clear of why we didn't use the multivariable chain rule? Okay, so the next thing is this one, dj dzhi. So here we can just forget about this if we like, and we can focus on this path. We know all of these dj dahis, and so what about this? If I focus on one of those, or if I focus on one of these, how many of these are involved? Well, this equation again tells us they're decoupled over I. So if I'm talking about this for one particular I, that only affects AH for the same I, not any of the AH for other I's. So again, we can focus on these not being sets, but just individual values, and we can do the chain rule without the multivariable stuff in it. Okay, so this we computed, and then DAHI, DZHI, we have this equation. For all I, we get this expression here. So that's done. Okay, so we've got the gradient with respect to all these purple variables. Is that part clear? Okay, so let's now move on to, for example, the gradient with respect to BO. So now you can see that for a single BO, it seems like we will have several variables here. Let's just check through the equations. So if I consider how I go from BO to J, this single BO affects all these different ZOs for the different I's. And all those different ones are summed to get the cost. So the path from here to here to here really does involve multiple I. So in that case, I really do need to use the chain rule for dj db bo. So here's the sum over the different i's in the batch, multivariable chain rule. Otherwise, it's just dj dzoi times dzoi dbo. So those individual equations are no different than on the last slide, so we are already evaluated this being 1, and so on. So that general idea is, of course, going to work the same way here. Between WO and J, you can see this single WO affects all these different ZOIs, and all those different ZOIs contribute to J. Something similar happens over here. If I look at this single BH, that affects all these guys in the middle, and so this affects all of those, and then all of those guys eventually are involved in this. So there too you have the multivariable chain rule, you have the summations. Okay, so what we'll do next time, we don't have time today, next time we will expand this to consider vectors instead of scalars, and then we will have to, again, it gets a little bit more complicated, we have to think a little bit more carefully about whether we have multiple variables or not, but it's sort of more of the same. So we'll save that for Wednesday. Any last questions on this? All right. Enjoy the warm weather and see you guys on Wednesday.